Okay, so I'm going to walk you through some more technical details about how buffer overflows happen and are exploited. And I'm going to do that in this class in the context of x86, 32-bit x86. So I know in like 61C you learn kind of a RISC-like language, but we're going to work with x86 because that's what's probably running on most of your laptops and desktops. But all of these flaws, for the most part, apply also to other microarchitectures as well. So your phones, there are variants of these kinds of exploits and attacks that apply to them as well. So let me talk to you through. But I want to talk about x86 because I want to be concrete and specific, one particular architecture, because then we can look at very specific details. It can be very concrete. So here's how memory is laid out in the x86 architecture. The memory, so with 32-bit architecture, so addresses are from 0 to hex. They're written in hex for convenience. FFFFF. And I'm going to write that vertically. So the smallest, lowest numbered addresses are at the bottom, the lowest. And the highest numbered addresses are at the top. And there's code of your program here. That's called the text segment. Another relevant thing is there's the stack. The user stack is at a higher level, higher numbered address in memory space. And the stack grows down. So every time you do a function call, it pushes something on the stack, and that stack, the bottom part of the stack, goes down. It writes something to the bottom part there and then moves the bottom part down. Okay? And then there's a heap. Whenever you dynamically allocate anything with malloc, that goes on the heap. And the heap starts in a different place here, and it grows up. So every time you allocate a new object, it gets allocated here, and then the high end of the heap goes up a little bit. So it's going, as time goes on, it's going up, 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 up. And then when you deallocate, it might go down, 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 and allocate goes up, up, up. Okay? In x86, there's registers. And we have a couple of different kinds of registers. There's registers named EAX, EBX, ECX, EDX. Those are general purpose registers. They'll be typically used to store values like integers or addresses. And then there's two special ones that are relevant to what I'm about to tell you about how the stack works. There's the EBP and the ESP. And the ESP is the stack pointer. It points to where you currently are in the stack. So each time you call a function, a new stack frame gets pushed on the stack. And ESP remembers where where you currently are in the stack. And if you push something on the stack, remember the stack grows down. So that means pushing decrements the address stored in ESP. ESP stores that address. And stores something in memory there. And if you pop from the stack, then you read from memory at the location specified by ESP, and then you increment the stack pointer to move it back up. Okay? Same thing with okay, so that's how pushes and pops work. And then EBP points to the start of the current call frame on the stack. So think of that as the start of this place where you would have things like local variables, basically. So this is probably easiest to show with a picture. Let me talk you through how a function call works, and then I'll show you a picture. The way a function call works is when you make a function call on x86, arguments are passed on the stack, not in registers like in some other architectures, but on the stack. So the caller first pushes the arguments onto the stack and then executes the call instruction to call the function. And the call instruction figures out the location in the code to return to and pushes that into the stack. That's the return address. So it pushes the return address onto the stack to remember that for when the function is done, this is where to come back to. And then it transfers control to the function. And the function does a whole bunch of stuff. Typically, at the start of the function, it does something called the, prologue, I guess? It saves some stuff. Like it saves the old value of the EBP, because it's going to modify that. And then it does its work, whatever work it's going to do. And then when it's done, it restores everything that it saved, so that things are back in the state that the caller was expecting. So like it pops the EBP to restore back to what it used to be. And then finally, the function executes the ret instruction, return, which jumps back to the return address that was saved up there, and returns control back to the caller. Okay. So next time I'm going to talk you through what this looks like visually, and then I'm going to show you, the reason why I'm showing you all this stuff is how an attacker who has knowledge of this can use this to create really nasty exploits of buffer overflow bugs. So on Wednesday, you'll see how to exploit buffer overflow bugs.